It's my pleasure to have with us Nirupam Roy. He's an assistant professor at the University of Maryland, College Park. During his PhD, he did some pretty fascinating work on attacking invisible attacks on Alexa devices, where he sent inaudible sounds and showed that you can actually make the smart speakers respond to them using ultrasound. So he's been doing quite some interesting work in the IoT space, in particular in drones, which he's going to be talking to us about today. So welcome, Nirupam. The floor is yours.
Thank you so much, Sham. Thank you for this kind introduction. Hello, everyone. Today, my talk is about acoustic perception in IoT, opportunities and perils. So let me start by saying this nice thing that we are surrounded by acoustic devices. Of course, we know that millions of Alexas and voice assistants have been sold, but that is only the tip of the iceberg. Various different kinds of acoustic devices are surfacing, which are smart and which are in our daily lives and which are connected to our daily lives. For example, Qualcomm is developing acoustic speakers which are smart enough to find the profile of our inner ear canal so that the sound can be customized for each user. Companies like Google, Leap Motion, they are embarking on fine-grained gesture recognitions using acoustics. There are various kinds of uh, sensors, on-body sensors. They can continuously monitor human bodily sound, and they are developing new kinds of biomarkers for detecting new diseases. Various other kinds of applications around acoustics that can fine-grain the directionality of the sound sources. They can understand our life better and provide various different kinds of uh, solutions. So in today's talk, I work on acoustics, mostly acoustics IoT. We call it Internet of the Acoustic Things. Uh, in this talk, first I will give an overview the of my group and what we are doing, uh, what are the projects that we have done in the past, and then we'll talk about two of the projects that is really showing the opportunities and perils that we have worked in recent past. So please feel free to stop me anytime during this talk and ask questions. If you have any doubt, please feel free to interrupt me anytime during this talk. So the fundamental glue that is enabling this new solutions around acoustics is the confluence between sensing, computing, and communication that is getting stronger and stronger every day. And in our laboratory at University of Maryland, College Park, we are enabling new kinds of applications through that. I'm fortunate to work with my graduate students. So the talk that I'm giving today, most of the materials are investigated and developed by Nakul, Ithaza, and Yang. And also I have worked with many masters and undergraduate students to develop, to explore this acoustic space more. So the main focus of our research is to develop new primitives in acoustics and vibrations. You know, vibrations is just another form of acoustic signals through solid. And we are enabling new cyber-physical solutions and human-centric applications through these primitives. So if I try to define the mode of our work, we start from the physical layer. We try to analyze the signals and develop various building blocks from those physical layers, uh, sensing signals from the acoustic devices, various radios. Those building blocks are like inaudible acoustic, vibratory modem, low power sensing systems, and then we combine those building blocks to enable various kinds of applications that targets voice interfaces, wearable devices. We explore security and safety of such devices, IoT devices, and also wireless localizations and energy harvesting. in doing so, we draw from principles in networking, embedded systems, and also uh, take advantages of various tools in signal processing, communications, and learning. If for this particular talk, I have categorized our work in two main categories where we have made and broken things. Making and breaking in the acoustic IoT space is what we do generally. So for example, we work on developing new perception system for drones using acoustic signals. At the same time, we look into acoustic eavesdropping using vacuum cleaner, robotic vacuum cleaners. And in one hand, when we develop inaudible sound for communication, we use that inaudible sound to hack Alexa or voice interfaces. In one hand, we have developed vibratory communication system. At the same time, we have shown that how vibrations can be leveraged to eavesdrop human voice. So lots of making and breaking are happening. Today for this talk, I promise to show the opportunities and perils of acoustic IoT. So I have sampled two of this project from this list, and I'll show that how we can use acoustic systems, acoustic sensing, for a better perception in drones, in resource constrained tiny drones. And I'll show that how robotic vacuum cleaners, which are so popular and we have welcomed them in our houses, will show the possibility of eavesdropping our private conversations using the LiDAR sensor in those vacuum cleaners. So these are the two projects that I have selected: low power acoustic perception to show the opportunities with Internet of Acoustic Things, and at the same time, the perils with acoustic eavesdropping. My research work focused on acoustic sensing and perception security. Today, I have picked the project so that we can show that how Internet of Robotic Things can get benefited, and also some words of caution with acoustic and robotic things. So let's get started with the first one. Please feel free to ask me questions anytime if you have one. So the first project is enabling self-defense in small drones. This is the paper that my student has presented in Hot Mobile 2020. So let me start by saying that drones are no longer recreational toys. Although it started its journey like a toy, but it is no longer merely being used as toys. Rather, they're being used in serious applications. In law enforcement, police use drones for surveillance to track cars which is not behaving right. If you recall, in 2019 Australian wildfire, drones, hundreds of drones were deployed to track if there is live, what is the spread of that fire, if there is any pocket where animals are stuck in, some kind of applications which was not possible even 5 years ago. And now we are taking advantage of this flexible, movable, and dynamic system that we call drone and UAVs. At the same time, recently in China, during the lockdown for COVID, drones were used to deliver essential objects, medicines, and food. Of course, we have heard of using drones as delivery services. So UPS and USPS are planning to use, DHL are planning to use drones as delivery cars. So lots of applications are around the corner, and we are planning to use drones for more serious applications. So millions of drones are already sold. The army is ready to serve us. But at the same time, when the applications of drones are getting serious, the threats are also lurking around the corners. Maybe attackers, and some of the cases have already been surfaced, that attacker can attack drones and for vandalism, for profit, for fun, and they can take them down. Uh, and at the same time, when we are thinking about whether robots are ready enough or autonomous systems are ready enough to be in our daily lives, we also need to think whether we are civilized enough to live with robots. So you can see that this pizza delivery robot is being invaded by a person for simply some fun. So the time to think about whether we need a defense mechanism for uh, UAVs or drones, because it is easy for someone to disrupt the performance of drones or simply take them down, because they have lots of rotor, they're trying to fly in the air. Little bit of collision can completely instabilize the system. And also their orientation tracking system depend on a series of state. It always try to maintain the state of the orientations and the speed that it has seen in past a couple of seconds. And if some sudden jerk or sudden collisions is happening, that orientation tracking system can completely go disrupted. It also equipped with lots of fragile structure that can easily be damaged. So basically, we are trying to ask the questions how we can prevent, how we can enable a defense mechanism for drones. And particularly, we are not, looking for any targeted attack, because drones are so fragile that it doesn't require a targeted gun or something to throw them off track. Even a simple thrown object that can disrupt their operations, that can completely take it down. Even if someone is playfully throwing a stone at a drone, they cannot defend itself and it can completely destroy the drone. So we ask the question, um, can we enable a defense mechanism for such drones? Isn't there any solution that can make this drone to identify if a flying dynamic object is coming towards it, and cannot it simply dodge of that obstacle? That's the questions we are trying to ask here. Okay. So the question, if we ask the questions whether there's any defense mechanism already available, of course we have many defense mechanisms. Right, radar has been is being developed for past 30 years, and it has been completely perfected to defend such aeroplanes or even small planes. There are other systems like countermeasure systems, large aircraft infrared countermeasure systems. So there are mechanisms to detect dynamic object that is coming towards a flying drone or flying aeroplane. But these are the heavy, big mechanism, and it's not suitable for drone. Why not? Because they have low weight carrying capacity. These are the tiny flying devices that cannot carry a lots of sensors with them. It has a small form factor. We cannot have lots of sensor and in form of an array to precisely detect in which direction the objects are coming from. It has limited power. We cannot waste too much of power in analyzing the signals and in order to provide a better object detections or situational awareness in small drones. And also it has limited computational resources that makes it really limited in order to this capability, how much it can do to process the data. Uh, Overall, it says that these constraints are, say, swap constraints, size, weight, and power. Basically, that limits what we can do or what kind of safety and defense mechanism we can build for tiny, small drones. If you take a look at the current research, the current trend in research for situational awareness in drones, you'll find that mostly it is trying to tailor the existing LiDAR-based systems or radar-based system or even camera-based system and trying to make it consume low power, somehow fit for these flying drones, and particularly for bigger drones, it still may work, but it simply doesn't work for small, tiny drones. And the reasons are the same. This kind of image-based system that consumes lots of power, relies on heavy computing and limits flight time. Cameras, particularly CMOS light cameras, they doesn't work in dark. So even if you forget about all the hardware limitations, etc., if we can only focus on what is the current trend of developing this situational awareness in UAVs, you'll see that we can generalize this trend as imaging and detection. It may use LiDAR, radar, or any other technique, but basically it's trying to find an image, find a video of the surrounding environment of that robot, and then it's trying to identify if some object is moving, at which speed is this moving, and whether it is coming towards the drone or not. This was a standard technique that was adapted and perfected for ground robot. In our lab, we are trying to break away from this core fundamental idea of taking a snapshot of the environment and then detect inside this, basically using some form of some variation of image processing to identify if an object is coming towards that drone or not. We argue that this is, first of all, this is not required. We can do better. And of course, it is not suitable for tiny resource constraint drones we are targeting to enable defense mechanism in. So our solution at very high level is to develop some event-specific sensors. If we call this LiDAR, radar, or image-based systems, are a generalized version of this situational awareness, taking the snapshot of entire environment. We are breaking away from that idea, and we are trying to pitch the concept: can we detect one specific event with some sensor? Can we build a sensor that will be dedicated for one particular event, and maybe that is sufficient for dealing with that thing, and it's particularly suitable for SWAP constraint devices. I will elaborate more on that, but let me tell what we are trying to achieve through this event-specific sensor. We do not need to, for this particular application, like detecting dynamic object that is coming towards a drone, we do not need to localize that object. Fundamentally, we do not need a scene imaging. We do not need the direction of arrival either. If we can find the direction of arrival of the object, it's good. But if we think it again, in order to detect if an object is coming towards the drone, and if the object is going to hit the drone, that is sufficient for the drone to know, and maybe with high accuracy, with high probability, dodge that dynamic object. So basically, we need to know if any moving object is going to hit me. The drone is asking the question, is there a moving object in the environment, and whether this is going to hit the drone or not. We need this one bit information. We do not need to take an image of the entire environment. We need this one bit information, hit or a miss. There is an object in the environment. It's a dynamic object. We are asking the questions whether this is hit or miss. If it is a hit, we need to dodge that object. If it's a miss, don't do it, just stay there, right? All right, so we'll talk about how we are doing that. But if we are successful to do that, it can create a new perception system, and it can enable some sort of defense mechanism in tiny drones and flying objects and tiny robots. So imagine that the small robots are being deployed in a disaster site before the actual force will be deployed, and their object is to go and chart the entire region. There will be debris flying off. They should be able to protect themselves even if we forget about a targeted object is being thrown at the drone. So we see potential in developing this kind of low power, simpler mechanism to find if an dynamic object is coming toward that, and if the drone can dodge that flying object. To this end, we are I'm going to talk about Doppler dodge. You can clearly see from the name itself that we are going to use Doppler phenomena of the frequencies. I'll talk a bit about that. And we're going to use this Doppler frequency shift to enable to extract this 1-bit information if a dynamic object is going to hit my drone or not. Okay, so first of all, I'll give you a brief introduction of what Doppler effect is. So if you recall from your high school physics, that Doppler effect is a phenomena where the perceived frequency is changed due to the relative motion between the listener and the source. And this source doesn't need to be a sound source per se. It can be a reflector of the sound source as well, because we know when a surface is reflecting sound, it behaves like a virtual sound source for that analysis. So if we have a speaker, imagine that the sensor that we are going to develop, it has a speaker and a microphone. The speaker is sending out the signal, and it is, let me see, I think I have questions on chat. I get a question, on such limited 1-bit information about the object limit autonomous drone navigation capability? Excellent question. So basically, let me paraphrase the question, whether if we limit our situational awareness to this 1-bit information, whether this is a hit or miss, don't we need such a snapshot or image-based system anyway for navigation? Most often than ever, there are various ways to do navigation, and we are separating this navigation from this defense mechanism. So navigation can be done completely in a blind mode, where it is running on GPS and it doesn't, or maybe in dead reckoning method using its inertial sensors. So essentially, if the drone is not using camera or camera-based system, then it doesn't require this camera or snapshot just for detecting dynamic object. Okay, and at the same time, even if it is using a camera-based snapshot system, still detecting a fast-moving dynamic object is difficult, given the frame rates of the sensing system. We have also tried the same thing. Our evaluations, we've run our evaluations with camera-based system, and we have seen that if the frame rate is not high enough, the system doesn't get enough time to respond to this fast-moving dynamic object. So you can see that anyway, this defense against the dynamic object requires a little bit of more computation, a little bit of more perception than traditional navigation systems. So I hope that answers your question. So let me get back to the mechanism of Doppler effect. our sensing system will send out a signal. It will wait for the reflection, that is, the sound will hit the moving object and it will come back to the microphone. It will analyze the signal to detect the direction or this one bit information, hit or miss. Okay? So we know that when this reflector is moving, this ball in this case, the Doppler shift happens when the signal is hitting the object, and also it will have another another level of Doppler shift because of the movement of the ball itself, right? So we will have two rounds of Doppler shifts, and the formula is simple. Delta F is equal to Fs, which is the source frequency of that sound source. Is 2Vr divided by V sound. Vr is the velocity of the object. Okay. Oftentimes, when we discuss this Doppler effect, we miss one part, that this Vr is velocity. There's one term that is we often miss, is the theta, the direction of the velocity. So if it is not directly coming towards the sensor, and if it is making an angle theta, then we need to make some corrections to Vr cos theta divided by V sound. Okay? So in this project, we leverage this particular part, this missing part, this Vr cos theta, which is dependent on the angle relative to the sensor, which means relative to the drone. So let me show you how this radial angle, we call this theta the radial angle, how this radial angle is going to affect our detection. Okay. So imagine when the object is directly coming towards the drone. In that case, the radial angle is not changing. So we always have V cos 0, which is 1. So we have a constant velocity, even for a small time. And if we plot the Doppler frequency for this constant angle, we'll find a constant Doppler shift. Of course, you can argue that whether velocity is changing over time, of course it is changing, but if you take a smaller snapshot of that entire event, for that time, given that the theta is not changing, velocity change is negligible, we can assume that the Doppler frequency shift is constant. But let's take a look at what happens when you have some radial angle, say theta. When you have a radial angle, which means that object is not coming directly towards the sensor, it has a constant angle from that. You see the radial angle is constantly increasing, it's constantly changing. It's not a fixed angle, which means the radial velocity is decreasing in an exponential order. So similarly, this increase in radial angle will make the Doppler frequency to change in exponential manner. So this is the key observation that we have leveraged here to enable this detection, hit or miss. So in case of a hit, we know that the Doppler frequency is not going to change for a certain period of time. It's going to hit the sensor. If the Doppler frequency is changing exponentially, it's going to miss. It is not going to hit the sensor. This simple observation, if we can detect this change or rate of change in the Doppler frequency, we should be able to get that one bit information whether this object is going to hit the drone or not. Okay. So this is the intuition. Next is the task that is left is how we can detect this change in Doppler frequency with a low power, less computation mechanism. Okay. Before we go there, let me show you the verification of this intuition. In order to show that, we have created a signal source, a microphone, and we use a Nerf gun to shot a bullet at our sensor. Here's the nerve gun. We are hitting this time, then the first time it's hitting the sensor. And we'll repeat this experiment while it is missing the sensor maybe by a few centimeters. If we plot what is the Doppler frequency for these two experiments, we can clearly see what is happening. You can see that the Doppler shift remains constant or horizontal line in case of when it hit the sensor. And for the second experiment, the signal is dropping exponentially. If we can detect that, we should be able to find our event sensor that can tell whether the object is hitting the drone or not. Okay, so let's see how we can do it without wasting too much of a computation cycle. Of course, we are going to divide the entire time frame into a small blocks of time, and we need to compare the frequency changes over time. And you can see that this is an iterative method. We are always comparing between two sensing block of time. If we divide this ft, frequency shift in time t, by frequency shift time t plus delta t, in ideal case, it will be 1 when it is going to hit the object, hit the drone. In the second case, it's going to be more than 1 because it's exponentially decreasing. The Doppler frequency is exponentially decreasing. That we call the radial drift. We have developed two methods. One is the basic, most intuitive method that is using FFT to find the frequencies and then comparing the frequencies in subsequent time slots. We have developed another method, which is frequency translation method. We have used it in analog domain, and we'll show that how with less number of computations, it can do the same job, where fast Fourier transform-based system can take much more power and computation cycles. So let me quickly talk about the basic approach. The basic approach is nothing but at every time slot, do the FFT and find the leading frequency, find the shifted Doppler shifted frequency, and then calculate the ratio, the radial drift ratio, to detect whether it's a hit or a miss. We ran this experiment for many different situations with different size of the object. And you can see that in the hit case, of course, it's not perfectly 1 because the velocity changes when it is approaching the drone, but it is pretty close to 1 when the hit case, for the hit cases, and it's certainly much more for miss cases. So we can clearly draw a line, a threshold to separate hit versus miss in this FFT-based approach. So unfortunately, doing continuous FFT for each time slot, it's expensive. Even even if it's actually significantly less compared to the camera-based solution, but still we want to reduce the power, reduce the energy consumption to the level that it will work with a very small drone, very small robot. So we propose something called frequency translation. The idea is basically, again, it's having the blocks of time, the slots of time, but instead of doing FFT in the time domain itself, it's multiplying the signal in 2 time slots. It's multiplying the analog signal. When we multiply this signal, you can think of this heterodyne multiplier. And in case of the hit, where we have the fixed frequency, unwavering frequency, we'll find that we have something called cos 2 pi 2FA. Of course, these two frequencies, FA is the shifted frequency. Given that these two frequencies are the same, we are going to have another frequency, but that is not changing over time. On the other hand, given we have a significant difference between these frequencies in these two time slots, after multiplications, we can see a lower frequency component and a higher frequency component. Of course, the higher frequency component is fluctuating. On the first case, if you can see my cursor, on the first case, the lower frequency component is 0 or almost 0. In the second case, the lower frequency component is significant. If we can detect this variation, we should be able to detect whether there's significant frequency change or the frequency is changing sharply over time that is leading to this low frequency component. Let me take a question. I think I have two questions here. Is there some way to handle the case that the object is not coming in directly, but can still hit the drone? Good question. So if it is hitting the drone, you can see that if the angle is more, then the exponential decay, exponential drop of the frequency is faster. So after we can detect the slope, after we can detect the drop of the Doppler frequency, we should find a suitable threshold in to incorporate the case that even if it is not directly hitting the sensor, if it is missing by 20 centimeter, then it's good enough to avoid any collisions with the object. So some sort of thresholding is required, unfortunately, but that can solve the problem of whether it is hitting directly or not. Okay, so let me quickly take another question now, and we can take the third question later. So after determining if an object will hit, how could the drone dodge if it doesn't know which direction of approach? That's a very good question. If it doesn't know how far it should move, then it's a problem. Of course, ideally we can think of if we can know the direction of arrival, then it can plan to dodge it in certain directions. But that is for a sophisticated mechanism. If you can know that if the object is going to hit you, and if it can quickly move out of that direction, if it can quickly move from that location, then with high probability it can dodge that object. And even for sophisticated dodging mechanism, oftentimes it doesn't get, even if it knows the direction of arrival, it doesn't have that much of time to precisely calculate the motion at which or direction of movement. So oftentimes it relies by something called reflex action. It's like in human, if you accidentally touch a hot plate, you will randomly, your reflex mechanism will quickly move your hand without consciously calculating in which direction it can optimally move the hand. So in our defense mechanism and the current work that we are doing, we are trying to incorporate this artificial reflex action where it is not very calculated in which direction it is going to move, but with high accuracy, it can dodge any fast moving object that is coming towards this direction. All right, so let's get back to this frequency translation based method. We have shown that in two cases, we have found a simple analog technique that can tell us whether the frequency is sharply changing or not. We can, once we find this frequency, we can sum up the time domain signal in the entire time slot, and we can repeat it over multiple time slots. We can see that in case when the object is going to hit the drone, then this summation, similar to our previous case, in the summation, the resultant value stays close to 0 or some DC constant value. In case of sharply decreasing frequencies, it is wavering. The low frequency component will surface through this multiplication and summation mechanism, and that variation can be detected with a simple DC signal detection mechanism. These two cases can be distinguished from one from the other. And again, in the same kind of thresholding method, we can find a clear separation between the hit and miss cases. So you can see the second method, it's much easier to implement in analog domain without requiring too much of power to handle the signal. And at the same time, given that we are not wasting time in running FFT and all, it's giving us much faster, much lower latency, meaning the much faster turnaround time to detect whether the object is going to hit or miss, which is a crucial information when we are trying to develop a defense mechanism. All right, so I will quickly skim over the evaluation. If you're interested, go and take a look at the paper. This is a work in progress, so feel free to contact me if you have more questions on that. So I will, in the interest of time, I'll quickly skim over this idea. So the evaluation, in the evaluation you can see we have used different angles, different size of object that is coming, different speed. We have used Nerf gun, thrown object by hand, etc. And you can see that when it's going to hit the object, meaning the miss by distance is 0, it's going to hit the sensor. You can see it has almost perfect output and perfect detection that it has detected the hit case. For the miss cases, we have tuned the sensor in a way that it is biased a bit towards hit cases so that it can avoid any collision. We can tune it accordingly, but in the current case, if it is missed by 50 centimeter, it is somewhat related to the question that I have just answered. If it is missed by 50 centimeter, then we can see that in certain number of cases, it is calling it as detection. It is certainly a problem of finding the perfect threshold. Of course, if it is far away from the object or far away from the drone, the dynamic obstacle, then we have much more miss detection rate. Multiple different directions we are hoping to develop. We are currently working on that. One of that directions is estimating optimal path. We are trying to find an analog solutions to find some hint about some gross hint about the direction of arrival without sacrificing the fast latency of the proposed mechanism. So the takeaway is that lightweight sensing inferencing modules to enable a way of self-defense in resource-constrained robotic vehicles and drones. I will stop, but I will answer some of the questions that I haven't answered before. So can't we extend the passive acoustic object detection concept by actively sending sound to explore the surrounding for building a collision avoidance systems like bats? Will power be an issue of this? In this, can we also combine sonar imaging with that? So first of all, we hope that we could use the passive detection system, but we cannot, because often we thought that the moving object will make some sound that we can detect and find the intensity, the directions from that. Clearly, it is not all objects make sound loud enough, so the hit rate is much more. And of course, there are some acoustic slams that is being used to map for the mapping and navigation system. But again, like I answered before, it requires a completely different mechanism to detect dynamic obstacle with that. Let me start my second project, which is acoustic eavesdropping. So this is the name of this paper. It's a Census 2020 paper. The name of this paper is Spying with Your Robot Vacuum Cleaner, the eavesdropping via LiDAR sensors. It is a collaborative work with NUS professor Jun Han, my long-term friend. And the most of the work is carried out in NUS and with a collaboration with University of Maryland with my lab. All right, so autonomous systems are everywhere. Like we said that acoustic systems are everywhere, so are the autonomous systems. We have self-driving cars, industrial robots, delivery robots, and vacuum cleaners. So of course, they need to navigate in their environment, like we have seen in our past project. Navigation is the biggest concern, how it can do it. So various different kinds of navigation systems and sensors are equipped in this autonomous system. And one of the leading sensor is LiDAR. LiDAR, light detection and ranging. It basically uses the laser sensor to send out the laser signal and listen to the, or actually analyze the reflected signal to find the distance of the nearby object. And basically it's a spinning laser sensor that can find the basically an image of the depth image of the entire environment around that sensor. So robot vacuum cleaners, like self-driving cars and delivery robots, robot vacuum cleaners, they are also increasingly using this LiDAR sensors for its accuracy. Uh, iRobot mostly uses camera-based navigation systems and infrared navigation systems, where Roborock and some other newer versions and newer companies on robot vacuum cleaners, they use LiDAR sensors. Our questions is basically whether this robot vacuum cleaners or these LiDARs are a threat to our privacy. If we look at from the acoustic angle, we are specifically asking the questions whether this LiDAR sensor can be repurposed as a stealthy microphone. We have let this vacuum cleaner to come in our environment, be in that space. Can this robot vacuum cleaners be hacked, and can they spy on our private conversation? That's the core question that we are asking, and we have shown that yes, it is possible. So if you think about the LiDAR sensors, it has a laser gun that is sending the laser signal. It has a laser sensor that can sense the reflected signal. With that, even if it sounds little weird how we can repurpose a LiDAR sensor to a microphone, let me tell you, it is not very surprising. And probably many of you have seen laser microphone, something called laser microphone. In old movies, they have actually really made it popular, but this is a real device that you can buy a laser microphone. And if someone, the idea is to shoot laser beam through a system. And if someone is talking far away from that place, from the sensor, and if there is any vibrating object nearby, like the window pane, which can get the vibration from the acoustic signal, it will move in accordance with the wave that is being generated, the acoustic waves. So the reflected signal will capture those vibrations, and it has a very sophisticated laser detector that can sense this movement to convert that laser movement to acoustic signals. Very sophisticated system. It does exist, and this is real. So we thought that if can we turn our LiDAR navigation system to laser microphones, because it has all the necessary hardware. Probably a little bit of tweak can make it a laser microphone, and if it is possible, then it is a threat to use those LiDAR based systems in environment, in our personal environment. So I have already mentioned how this movement is changing the phase of the reflected laser signal, and also changing the intensity of the reflected signal as it is received by the sensor. So if this phase and the intensity can be carefully analyzed, then the movement can be detected, which is proportional to the wave, variations in the wave, which in turn is proportional to whatever the person is talking, or whatever sound is being generated in the environment. So the recovered signal will have almost one-to-one accordance with the spoken sound. In our work, LiDAR phone, we have used the daily object or nearby object, just like a waste bin basket, or it can be the table, the legs of the table, or any nearby object that can respond to the vibration of the sound that is being generated. The sound can be generated from human voice. It can come from our personal laptop, and it can launch various different kinds of attacks. In this project, we specifically focus on numbers because, as I will explain later, we have shown that it is not possible to run a speech recognition algorithm to understand whatever is being spoken, but it can, with very high accuracy, it can identify which numbers are being spoken. So if you are sharing your social security number or credit card number, the potentially the vacuum cleaner should be able to listen to that and share it with the attacker. So we will focus on, if we, before we going into the details, if I try to explain what is the attack model, then the first thing that we need, that the remote attack, the vacuum cleaner is compromised, and it is connected, oftentimes it is connected to the cloud for better controllability and mapping. And various other work has shown that this kind of connectivity can be hacked, and the robot vacuum cleaner can be given instructions or even man in the middle attack. So instead of going too much into the attack part or how this system can be hacked, we have focused on this perception, how we can recover sound from these laser sensors. That is the core idea of this attack. So the threat model, like I said, we will be focusing on a few discrete information like spoken digits, speakers, gender, identity, or if something is being played from your TV, if you are watching CNN versus some uh, other channel, it can find your political orientations from those sound. So as you can see, we are particularly focusing on pattern matching based attack from the recover traces of sound from this LiDAR sensor. So of course, we are assuming that it has a vacuum cleaner, TV, and object nearby where the laser can be pointed to recover the sound. Okay, so LiDAR, which relies on the laser for the hardware of the laser is already in that. We are combining it with the principles of laser microphone to enable this attack. First question that comes to our mind, is this a done deal? If we have the LiDAR sensors, if we know how laser microphone work, is that all? Is it going to solve the problem, or do we need to do something else? Of course, it's not all. We have seen, we will show multiple challenges to realize this attack, but none of the challenges is super difficult that an organized attacker cannot launch it. So let's start by how this laser sensor in laser microphone is different from a LiDAR sensor. So when we hack a laser LiDAR sensor, we basically get two different kinds of signal from it. Number one, what is the distance of the nearest reflection or the reflecting source or nearest object? What is the distance of that object from the sensor? And we cannot use it for our LiDAR phone because it is not carrying any information, although you can argue that at some final level it is vibrating, so the distance is changing, but the laser LiDAR sensors are not sensitive enough to pick up that tiny vibration, the micro movement of those objects. The distance changes, small distance changes due to that vibration. So we have no hope there. So we turned our focus to the other information, which is the laser intensity reading. So the LiDAR, at the same time with the distance reading, it is also constantly sending the laser intensity. And interestingly, this laser intensity will vary depending on the vibration of that object. We have found that even if it is vibrating at a very fine grain level, still we can recover enough variations in the laser intensity that is enough to recover some traces of the spoken sound. So the first challenge now is in any of this kind of, if starting with the first challenge that we run into is the low signal to noise ratio. The SNR of the recovered signal is really low. Why it is low? Because if we compare it with the laser microphone, where it is directing it to the window, which is a specular reflection, it is a shiny, even surface, and most of the energy reflected in the one specific direction. Unlike that, we are dealing with everyday object that has rough surface, and it is causing a diffuse reflections. Only a fraction of the total energy is coming back to the sensor. And for distance finding, maybe it's good enough. The LiDAR can still work with that, but for detections of small vibration due to sound, that is not enough. So specular reflections is desired for laser microphone because they are also, that principles is also analyzing the phase difference in the reflected signal. But for LiDAR phone, we are dealing with some uh, scattered reflections, and we try to use some specular reflections where most of the energy is coming back to the sensor. Unfortunately, the sensor is not designed for that, and it goes into some saturation. So the sensor, if too much of reflected signal comes back, then it cannot function well, the sensor gets saturated. So all the variations due to the vibrations goes above the saturation level, and the sensor cannot detect anything. So we are stuck to the diffuse reflections and with the low SNR signal. Okay, so this is the hardware saturation limit. We need to have the reflected signal intensity below that threshold so that we can observe the small vibration, small variation in the reflected signal. Okay. Second challenge is actually even more fundamental. We all know that the LiDAR is a rotating laser, right? Which means it is not unlike the laser microphone. It is not directing its beam in one direction and sampling it with high frequency. It has 5 Hz rotation rate, which means if you need to sample one location's one object, you are basically getting 5 Hz of sampling rate. That is clearly not enough. So what we need basically for better detections of human voice and analysis, we need at least 5,000 hertz of sampling rate, which means 2.5 kilohertz of bandwidth. Clearly, that is not available here. So we tried to hack the system. You can find the details in the paper. We hacked the system and we stopped it to point the laser in one direction, which cannot be detected by the user. Users cannot notice anything, but for a fraction of a second or maybe for a couple of seconds, the laser will point towards a single direction and it will collect samples from that. But even if we do that, we could go up to 1800 hertz, which is clearly much, much lower than our required 5000 hertz. So how we can deal with this low sample rate, low resolution, along with low SNR, that is what we will quickly touch upon in this talk. Okay. So the system design, we have 2 phases. So one phase is happening, the first stage, which is bootstrapping, that is happening with a separate LiDAR sensors or separate vacuum cleaner in the lab of the attacker, if you will. And the second phase is the attack phase, where it is using the information that it had collected from its own laboratory experiment to apply it to one of the user's household Roomba or household vacuum cleaner. So in the bootstrapping phase, it is using lots of training data and applying pre-processing and trying to get some weightage neural network to train for different spoken digits or any other patterns of signal. uh, for example, it can find the jingle of a TV show to identify which TV program you're watching now. So once the training set is ready, in the attack phase, it is collecting victim pitch from the vibration and from the variation in the laser intensity and applying pre-processing and running through a prediction algorithm to classify which of this pre-trained sound it is trying to detect. It is trying to classify the spoken sound in one of those categories, and if it is cannot match it any of these categories, it says that it's unknown. So we basically boiling down the entire problem to a learning based classification method. We will show you the signal why this kind of neural network method is kind of unavoidable for this attack. Okay, so the first phase, the pre-processing technique, excuse me, that is dealing with this low SNR problem. And the second phase is the dealing with a low resolution problem or low resolution challenge. So the first, for challenge one, the goal of this pre-processing stage is to increase the SNR as much as possible. It is applying some noise, it's applying some correlation of the sound signal and some other technique that I will not go into the details, but I'll show you the result. How does the result look like? So on the right, you can see, on the left, you can see if we record the signal with a microphone, regular microphone, how does the spectrogram frequency, time frequency plot look like? And on the right-hand side, we are showing that what the laser LiDAR sensor recovered signal look like. So this is the initial sensors. You can see that we cannot understand, or we cannot see anything from that sensor. And it has a strong frequency anomalies that is suppressing any other signals to be clearly visible. So in order to do so, first of all, we have removed this strong reflections, a strong spectrum that you can see, a constant value that you can see on the spectrogram. And later, we are applying some sort of outlier removal and interpolation method to recover the faint patterns of the harmonic patterns of human voice out of that laser signal. And in the third stage, we are filtering it much more to reduce any other noise that is mostly concentrated in the higher frequency. Here, higher frequency I meant is more than 500 hertz. So basically what we can barely look at is the fundamental frequency of human voice and a little, maybe a couple of harmonics from the fundamental frequency and nothing more. So although it's doing a nice job in recovering the fundamental frequency and one or two overtones, but still it is not sufficient. In one of the demos, we have shown that how this sound actually, you cannot perceive anything from this recorded sound. So there is no hope that we can apply some sort of speech recognition method on the top of that. So here, these are the spectrogram for two spoken words, 7 and 8 spoken numbers. You can see that the fundamental frequency is clearly marked, but it is so noisy that if I could play the sound, you could hear that it doesn't even sound like 7, 8, or any other word. But there's two insights. Number one, the low spectral resolutions is making it non-intelligible even to humans. We tried to run it through the speech recognition method. It is not going to work. It will work to some extent if we can train the system with the specific person's specific sound signal, which is not a very practical attack. So we move to the second observations, where that even if the fundamental frequency is only barely visible, still for different spoken word, there are significant variation in that frequency band. If we can identify those variations, we should be able to classify the spoken word to one of the small set of words that we are targeting. And that's what we have done. So I'll not go into the details of how this convolutional neural network is designed. We have given it in the details. The evaluation setups show that how we have evaluated it. I will skim over this. One point is that we have tried various different kinds of household object, and we have shown that result, which has given more than 90% accuracy in detecting and digits. And also we have identified gender and other markers, other informations about the person, about the program that is being played in nearby TV. So one point of discussion is that not only it can recover sound, with the map of the movement of the robot, we can integrate, make this kind of attack more severe by clearly pointing out to one specific region of in our household. So that's all. We are working in this cyber physical system, wireless, personal computing, mobile health, where acoustic has lots of potential, but at the same time, I'd like to warn ourselves and the users that about the perils of this system if not designed well. So that's all. Thank you so much for listening in.
Thank you so much, Nirupam. This is very, very interesting. We have a lot of questions, so I want to make sure that we have time for that.
Sure.
So Ton had a question, which is, increasingly we are seeing that phones and other things are starting to have LiDAR.
Yeah.
So what does that mean? Like, can you also use those kind of consumer grade LiDAR devices on smartphones to mount these kind of attacks?
So like we have shown in this paper, yes, it is potential. There are some potential risk of using this as side channel for eavesdropping sound or any other information. But at the same time, while uncovering these threats, we are also looking into ways to thwart that kind of mechanism. So one way to prevent this kind of attack is to have a security layer just after sensing layer, so that we can add some kind of noise that is not degrading the perception or the actual detections of the signal, but it is to some extent reducing the eavesdropping possibilities.
Haunan had a question on what is the detectable range of the specific system? Can you be pretty far away, or do you need to be really close to your dustbin?
So actually, we have shown that it is working for 1 meter to 1.5 meters. At the same time, these LiDAR sensors are not designed to work map far away object. It is anyway designed to detect object within couple of meters. So the eavesdropping will work up to the point where the LiDAR itself is designed to work.
I see. So the other question from Alex is about the motion of the robot itself. You talked about how the laser itself is scanning the surface and you disabled it. But can you do this when the robot itself is moving a little bit, or is that going to be challenging given the noise of the robot itself?
It is really nice question. So when we try to move the robot while it is actually fixating on one point, is too much of low frequency noise, particularly the low frequency region that we are looking into. So it is definitely a challenge. So we stopped the robot and pointed to one direction. So we did not show the result with the dynamic robot.
So we're going to move back to the first topic which we talked about, which is
Sure.
the self-defense for the drones. I'll start with the question I had. We talked about LiDAR, right? In the second talk, in the second part of your talk, and we also know that people are using LiDAR for autonomous vehicles, for collision avoidance and so on. And those, and in fact, like a lot of the LiDAR on phones are actually pretty small these days. So wouldn't that be a more natural fit for figuring out if someone is throwing something at the drone?
So like I mentioned in the talk itself, there is definitely it is possible to this kind of image-based processing. So some variations of the image processing can certainly detect if the object is coming towards the robot. But the question is, there are many others work in the vision community as well that show that if the sensor doesn't have high enough sampling rate, for example, when the robot is moving, it's moving at much slower speed than the incoming projectile. So for that purpose, the LiDAR doesn't need to scan the entire region fast enough for its movement, for its navigation. But when we try to use for a defense mechanism, it needs to sample maybe 5 times faster, which is going to consume a lot more power. We are looking for a low power solutions compared to that.
Interesting. So Anran had a question on the noise. In particular, when the drone is flying, there's propeller noise as well. And that can increase the noise floor and impact the accuracy of Doppler sensing accuracy. And did you see that?
Yeah. Actually, we have looked into that. So there are 2 kinds of noise that can come. Number one is the direct sound itself of the propeller, but we can cleverly left out that frequency band because it's very narrow frequency band, and we can look for other frequency band to operate. The second noise is actually a bit severe because of this motion, the constant motions of the propellers, which is also changing their speed. There will be some inherent Doppler all the time that is coming to the sensor. So we tried with the moving propeller itself. We need to find the right frequency band, and given that it has some limits on the total Doppler shift, we can contain the entire band in our region of interest, and we can avoid all these unwanted Dopplers. So that's how we avoided these issues.
So I think there's a question which I think Matthew asked, but maybe a little bit more generally, which is, you talked about, which is really cool, that you could throw the ball and you could tell that the Doppler effect was much more significant when it's directly in the angle. In real life, you're going to have so many different objects in the environment, and they're all going, I mean, there's walls, there's going to be windows, there's objects which are all going to reflect, and you're going to see Dopplers of all kinds. So how do you distinguish between, and in fact, like if a drone is flying towards a wall, it'll look from the drone's perspective, it'll look as if the wall is flying towards it at that particular velocity. So how do you account for all these issues?
So that's really apt question. So when the drone is moving and we are applying this kind of defense with Doppler, the entire environment is moving object with respect to the drone. But note that there is a difference in the speed of the drone and the incoming projectile. So again, the Doppler shift and the frequency, we can design those systems to avoid based on the speed of the drone itself. So if it is moving, if the drone is moving at X meters per second, then we exactly know that where all the Doppler frequencies are going to fall from the static object nearby. But it requires a bit of designing. The question is a really valid question.
So Ethan has a question on, can the system detect multiple incoming objects at once?
So that is a nice question. We did not try with multiple incoming object. The reason is it will definitely will work if we are applying FFT based system where we can distinguish multiple traces of Doppler changes. But for this low power frequency translation based analog system, that is a little difficult to deal with multiple objects at the same time while we are applying that. So this is something we are looking into. We do not have a solution for that yet.
So on a related note, we keep hearing, or used to hear these news about some of these military drones being downed in some of these militarized zones. Um, so it seems like it's just not the specific tiny drones you're talking about, but even the slightly bigger ones potentially have that issue. Do you know what the problem there is? Is it the same thing of missing some of these incoming attacks?
So basically the point, we have actually done quite a bit of literature survey, and the main point is how much sampling or how fast we are analyzing our environment. So in the questions of situational awareness, it boils down to the the speed of our sensing system versus the speed of the projectile, and the gap between them is severe. Oftentimes these systems are tuned to operate at the lowest possible sampling rate, lowest possible capacity, to save energy. And given that the kind of system we are using, those are inherently power consuming, inherently bulky. So saving energy when it is not required is for foremost priority. Those are the gap that is making those issues, that even if it has some mechanism, defense mechanism, it's not being able to detect fast objects.
We have two more remaining questions before we can let you go.
Sure, yeah,
Jan has a question on for the second project. What can you do to protect those who are less technologically competent? Is there anything else you can do besides recommending against purchasing these smart products?
So basically, we think that the liability relies on the manufacturer and the community in general. The users can raise the awareness, they can show the concern, but I don't think that at the consumer level we can do something to prevent ourselves. We can prevent one or two problems that is obvious to us, but making them panic for using those technologies is not the direction that we want to push them into. I think that the responsibility is on the shoulder of the manufacturer. They need, and the researcher as well. They need to identify it. They need to find the preventive mechanism to avoid that attack.
So Alex has a question, which is kind of interesting, which is thinking of your the drone dodging project. If you start thinking about adversarial attacks, which basically exploit your mechanism to kind of like make the drone behave erratically.
Right.
One of the adversarial attacks which Alex proposed is, for example, let's say I try to simulate the Doppler effect by a static object
Right.
and
Right.
kind of confuse a drone to do erratic things and as a result crash.
Yeah.
Um,
Excellent question. Excellent question. So one can, I mean, let me give you another example. One can actually send a signal constantly at the frequency where the drone is expecting the Doppler shift. And if it is constantly sending it, the drone will always think that some object is going to hit it. It will try to dodge it erratically. So it is a very nice question. Now, notice that although we haven't tried, we have been thinking around that. We can do some kind of preventive mechanism for that as well. Given that we are generating our own signal, this defense signal for Doppler shift, we can use some frequency hopping. It doesn't need to be a particular frequency. It can constantly change between multiple frequency, and it can undo with a specific coding. It can undo that frequency hop after receiving the signal. So that can be one way to deal with this kind of attack against this defense.
that is really cool. And because the adversary might not know the frequency hopping sequence, they might
Yeah,
not be able to, the probability of them attacking it is low.
yeah, that's exactly
Really
right.
cool. Sweet. Thank you so much, Nirupam. We took way too much of your time, a little bit over time as well. So thank you so much.
Fine. Thank you
Uh,
for having me. It was fun to be here and particularly meet you. So thanks so much. Bye
Thanks so
bye.
much. Bye bye.